There are many different force microscopy techniques based on the AFM, such as MFM, EFM, KPFM, etc. Magnetic force microscopy is a microscopic technique whereby magnetic properties of the surface can be imaged. This is more commonly known as the MFM. Consider a body with magnetic inclusions. The magnetic inclusions will generate a field close to the surface. A cantilever coated with ferromagnetic particles can interact with this field to form an image. Like the AFM, there are two major modes of operation, the static and the dynamic mode. In the static mode, force measurements between the cantilever and the surface are made, and in the dynamic mode, force gradient measurements are made. The static mode is not so accurate because force measurements generally tend to be small, while in the dynamic mode, since the force gradient measurements are much higher than the force measurements, it provides a higher signal to noise ratio. Hence, dynamic mode is preferred over the static mode. When the cantilever is near the surface, that is, at a distance less than 10 nanometers, it is under the influence of van der Waals forces and magnetic forces. But when the cantilever is raised to a distance approximately around 20 nanometers or more, it is primarily under the influence of magnetic forces. Since the van der Waals forces are much higher than the magnetic forces at distance less than 10 nanometers, the image consists mostly of topological information as well as magnetic information. Thus, it is common to obtain an image from an MFM in the lift mode. In the lift mode, a cantilever is initially brought close to the surface, that is within 10 nanometers, and with the feedback control switched on, the topological information of the surface is obtained. Then the cantilever is raised to a height called as the lift height, and the feedback is switched off. The cantilever then retraces the topological information that it obtained in the first run to obtain all the magnetic information of the surface. So where does the contrast in the images come from? The interaction between the magnetic tip and the stray magnetic field leads to contrast formation. Consider a domain aligned in this direction. Magnetic tip. The magnetic tip itself has a magnetic field around it. When the magnetic tip comes close to the domain, it is possible that the domain itself gets inverted. Thus, there could be a change in contrast within a single image. This is generally an artifact of MFM. As the tip passes through the sample, the tip sample position could vary. This variation would reflect in the makeup of the image. There are three major categories for contrast formation. In negligible modification, the tip does not interact much with the sample and there is very negligible change in the tip sample position. In this case, the contrast is a function of the magnitude of the stray field. In reversible modification, as the tip passes through the sample, the tip sample position is modified and it reverts to the initial state after the pass. In this case, the contrast is a function of the tip sample position. In irreversible modification, the interaction of the tip and the sample causes an irreversible change to the tip sample position. In this case, the contrast is not only a function of the current tip sample position but also of its previous state. In general, attractive interactions between the tip and the sample result in darker parts of images, and repulsive forces between the tip and the sample causes brighter images. Bits inside a magnetic hard disk could be stored with their magnetization direction parallel to the plane of the film. This is known as in-plane magnetization, or could be stored such that the magnetization directions are perpendicular to the plane of the film, called as out-of-plane magnetization. In the case of in-plane magnetization, the contrast of the image is from the walls of the domain. Thus, a single bit will be represented as a pair of dark and bright lines in the image. In outer plane magnetization, the bit itself is responsible for the contrast. In this case, the dark and bright bands in the image signify the on or off state of the bits. The resolution of the imaging technique depends on the tip used. Thus, it is important to select the right tip for the job. The obtainable resolution of MFM is inversely proportional to the active tip volume, and the sensitivity is directly proportional to the active tip volume. Thus, it is not possible to maximize resolution and sensitivity at the same time. Thinner tips have a lower magnetic moment but can create a highly resolved image. Thicker tips have a higher sensitivity as a large moment causes them to deflect more in the presence of small fields. A typical resolution of an MFM is around 20 to 15 nanometers, and for high resolution techniques, it could go as low as 10 nanometers. Magnetic resonance force microscopy is a technique that combines MRI and MFM. Modulated radio frequency waves are used to invert nuclear spins inside a sample. As the spin configuration changes, it creates a periodic oscillation of the magnetic tip. In some configurations, the tip is kept stationary and the sample is mounted on an ultrasensitive cantilever. The amplitude of oscillation so achieved is on the order of attonewtons and requires specialized instruments to quantify. MRFM enables subsurface imaging and also 3D imaging of the sample. The MFM technique has a wide range of applications. It is used by magnetic disk manufacturers for the design and quality control of hard disks. Also, MFM finds applications in studying magnetically active biological samples and superconductors. Real-time hysteresis curves of nanostructures and magnetic inclusions on the surface can also be obtained using MFM.